Hello, physics students. Today we're going to look at a horizontal launch mini lesson of a marble that rolls across the table and leaves the table with a initial velocity of 1.4 meters per second. The other known we have is the distance. It hits the ground 0.56 meters away. So I'll draw that in. Distance equals 0.56 meters. Now we have enough information to solve for the height of the tabletop and also the velocity right before it hits the ground. To do this, we're going to identify some hidden values and also some really key concepts. So in doing so, I'm going to pull up my chart here. You're going to see this from time to time in these problems where we're going to label out what's happening in the x and what's happening in the y. So to do this, we're going to kind of use this as a guide for our problem solving. So a couple key concepts that I want to go over with you relate to the horizontal velocity. So as you're looking at the horizontal velocity and the path of the projectile, once it leaves the tabletop, will be this parabola, this arc. And all points along that path, even if I take a look at the ball right in the middle, the velocity is still horizontally going to be the same. There's no horizontal acceleration. That's what makes it a projectile, 1.4 meters per second along the whole path. Even right before it hits the ground, it's going to have the same horizontal velocity, 1.4 meters per second. So we know that the horizontal velocity doesn't change. In the beginning, it's 1.4 meters per second, and way at the end of the path, it's also 1.4 meters per second. We can use this information to help us calculate some other things. So I want to break apart the motion in both the horizontal and the vertical directions, because in this case we're actually trying to find something vertically. We're trying to find the vertical distance, or the dy. To do that, we're going to need to know some information about the motion in that vertical space. So because it's a projectile and we know that gravity is acting, we can treat the vertical part just like a free fall problem, where we know that the marble leaves the table and it's as if it was to drop straight down. The y velocity will increase because of the acceleration of gravity. Therefore, we're going to want to use our kinematic equations to solve this. So for the vertical motion, in this case dy, we can use our kinematic equation. Dy is equal to the initial velocity in the y direction times time plus 1/2 times the acceleration of gravity times t squared. Now we know the initial velocity in the y direction. It starts from rest. So that term can already cancel out. What we don't know is the time it takes to fall. So we need to use our horizontal to help us calculate that time. The time is the same for both the horizontal and the vertical. To help us solve this, we're going to take a close look at the fact that the horizontal velocity is constant over the entire journey. Knowing that, I can use our equation velocity is equal to the displacement or distance divided by the time. Rearranging for time, I'm going to have the distance traveled divided by the velocity. In this case, the distance traveled horizontally was 0.56 meters, and the velocity was 1.4 meters per second. We're solving for the time. When I divide those numbers, I do get a time of 0.4 seconds. That 0.4 seconds is equal to the time for both parts, the horizontal and the vertical part. In all these problems, that is a key idea, that the time can be used in each part. So let's go back to our chart. Let's fill in some things that we know. We know the distance traveled horizontally was 0.56 meters. We know that there's no acceleration in the horizontal. We know that because the velocity did not change. We do know there's an acceleration in the vertical of negative 9.8 meters per second squared. The final velocity we don't know, and we are now able to calculate the distance. So we're going to be looking for these last two components of our problem using the information we have. Going back to what we talked about in the beginning, we'll substitute in now for my dy, we'll substitute in what we know. I can now use the information to solve for the height. So I'm going to rewrite the equation for dy as 1/2 gt squared. I just got rid of the term that had the initial velocity because that was 0 anyway. I'm going to use the information that I know. So this will be 1/2 times negative 9.8 meters per second squared times the time of 0.4 seconds, and that number is squared. When I run through the calculator, it ends up being a negative 0.784 meters. That tells me that it went a distance downwards, the negative sign tells me downwards, of 0.784 meters. Or in other words, the table is 0.784 meters high. So now I can go back to my distance and my y, and I know that to be 0.784 meters. The last thing I'll want to find is the final velocity when it hits and impacts the ground. If I go back up to my diagram up here, my sketch, I'm going to zoom into that point right there. I know all points along this path, the vertical velocity was accelerating. It started out as 0, and then partway through we gained a little bit of vertical velocity, and then at the very end, right before it impacts, it has its biggest amount of vertical velocity. That vertical velocity combined with the horizontal velocity will produce a resultant vector. And we're going to be looking for that vector to be our final speed right before it hits the ground. It's made up of both x component and y component. So I'm going to redraw that down on the bottom, and then we can calculate what that y component is going to look like. All right, so we know for the ball hitting the ground, so we're going to have our horizontal velocity. We already know what that is. That's the 1.4 meters per second. We're going to have some sort of vertical component going downwards. We don't know what that is yet. That's my Vy. And that's going to combine together, tip to tail, to end up with the overall velocity. So these are the components that we're going to find. We can even find then an angle of where that velocity was striking the ground. All right, so those types of things we can look for. So in order to find that Vy, we're going to have to use the fact that the object is accelerating, and it's accelerating over that whole path. So we're going to want to come back to what we know for our kinematic equation. Okay, to find this final vertical velocity, we actually have two options because we have both the distance and we also have the time. So we could use either one in order to solve this equation. I'm going to use the time and acceleration. So once again, going back to what we know that the initial velocity in y is 0, so this term can drop out, and then my final velocity in y is equal to the acceleration times time. In this case, the acceleration was 9.8 meters per second squared. We can keep that as a positive, or actually negative, times the time of 0.4 seconds. This ends up then being a negative 3.92 meters per second. The negative tells me that it's going downwards. So when I go back to analyze my triangle here, I know that my Vy in this case was negative 3.92 meters per second. My Vx was 1.4, and now I can use the Pythagorean theorem to solve for my resultant, solve for the red variable. So then V becomes the square root of 1.4 squared plus 3.92 squared. I just got rid of the negative because it's going to be positive. after you square it. Calculating that through, my final velocity is 4.16 meters per second as it hits the ground. So going back up to the very top here, we can kind of fill things in now. My final y velocity was 3.92 downwards, so negative 3.92 meters per second. And I now know the velocity right before it hits the ground was 4.16 meters per second. And I know the height of the tabletop was exactly 0.748 meters. I'm sorry, 84 meters. All right, thank you. Just to recap with this type of problem, remember to draw a sketch. They're really important. They'll help you figure out what's happening in the problem. Use the variables to label the different parts of your sketches. Start to fill in your x and y table with what you know in terms of the theory. So we talked a lot about the horizontal velocity being the same for the whole path. That means the acceleration horizontally is 0. In y, however, the object is accelerating. Gravity's pulling on it. So the acceleration is downwards at 9.8 meters per second. Therefore, it will have a different final velocity after a certain time interval. We can then use the horizontal equation to solve for the time, then use that time back in the vertical equation to solve for our vertical distance. We put both of those together to find our velocity, and finally put both components of the velocity together to find out what the resultant velocity was right before it hits the ground. Thank you.